the second part of 6.9, intermolecular forces. Now this section ties in and goes beyond what we were talking about in the last video about polar molecules, and it's going to tie into stuff we're going to talk about later, like even at the end of this semester when we're talking about DNA, or even before the end of the semester when we're talking about why does something dissolve in something else, or even sooner of why is something's boiling point higher than the other. It all has to do with the attractive forces between molecules. So our learning goal is to describe the intermolecular forces between ions, polar covalent molecules, and non-polar covalent molecules. So we're going to start with the very weakest ones first and work our way up. So if it doesn't have any other type of attractive forces, which so far we haven't talked about them, so we're going to start at lowest, then the default is the amount of electrons. Why? Because electrons are negatively charged. So, you know what? You have some negative things inherently running around in your molecule or your atom, whichever one. And so if these negative things happen to bump into another one, they're going to shift the electrons to the other side of the atom or the molecule. And when they do, it's going to cause a slight temporary dipole. So the electrons are going to be on this side, so it's partially negative, which makes this side of our molecule slightly positive. Whoa, as soon as we have a difference in charge, then another molecule or atom can be attracted, the electrons that are negative can be attracted here. And so because of that temporary dipole, then there can be a slight attraction. Think of it as magnets, like just a teeny tiny magnet here. Now, if there's not a whole lot of electrons, then that teeny tiny magnet's not enough to keep these molecules together for very long. And so you're going to have gases at room temperature for items that only have dispersion forces that don't have a lot of electrons. So arbitrarily, I'll just say something with less than 50 electrons total within the molecule, then it's probably going to be either a gas or getting close to maybe a liquid at room temperature. But, you know, it's when you only have 10, 15 electrons, then it for sure is going to be a gas. Now, we don't need to remember those numbers exactly. We just need to know the concept. If it doesn't have a whole lot of electrons, it's not going to be able to have a temporary dipole between these atoms or electrons, and so there's not going to be very much of an attractive force. If there's not much of an attractive force, then they're going to be separated, and they're going to be gases at room temperature. And they're going to have a really low boiling point because they've already boiled. All right. Well, polar molecules, such as HCl, are polar because, if you remember in our last section, when we did the electronegative subtraction, Cl was 3.0. Let's go right here. Our Cl is 3.0. Hydrogen is 2.1. When you do that, that is 0.9, which we determined as polar. Now let's go back and see if we can remember what the polar meant. That meant the electrons hung out here around the chlorine more, as evidenced by this arrow that's showing here. And so that's going to induce, it's going to be there a partially negative charge because those electrons, i.e. negative, are hanging out there. Doesn't have to wait for the molecule to sit around and hit another molecule. It's already there. And so, as we look at this picture here, notice we don't have to sit around and wait for them to hit each other. There is already this attraction of one molecule's negative to the other molecule's positive. And so these attractive forces are called dipole-dipole. Why? Think of the word polar. We identified them already as polar molecules. They have these dipoles where the positively charged end of the dipole in one molecule is attracted to the negatively charged end of the dipole in the other molecule. Well, if it's small, then it's still probably going to be quite often a gas at room temperature, but a lot of them have enough attractive pull that it would be a liquid at room temperature. Now, you may go, well, what about the electrons? Well, the electrons are not that much that we don't have to say, oh, they've got dispersion forces. Yeah, they do, but the dipole-dipole is so much stronger, it beats dispersion forces hands down. As we get more and more attractive forces, though, here, and more dispersion forces, then we would get a liquid. Now, water, yes, we determined that an OH bond was polar because our oxygen, if we think back to it, oxygen is 3.5 and hydrogen 2.1. So when you subtract those values, we're going to have a 1.4. So that's a fair amount of difference. Well, it's more than that. We actually have 2 of these bonds on a molecule, and they are not linear. It's not like they're going to be linear and cancel out. Because of these unshared pairs of electrons over here on oxygen that we haven't really talked about, but it has them, then these vectors are not going to cancel each other out. They're just going to kind of like add to it. So this special bonding, when hydrogen is attached to oxygen, nitrogen, or fluorine, and why those special ones? Well, because it has to do with 2 things. It has to do with their electronegative difference, and it has to do with the unshared pairs of electrons around the other atom, which you may go, what are you just talking about with unshared pairs of electrons? We didn't cover that. I know, that was one of the sections that we skipped. All right, we're not going to go there. Just realize that they do exist, and they make a very, very big difference. Now, those dipoles on water are so strong, we don't even call them dipoles. They have this special name called hydrogen bonds. Now notice, hydrogen bonds are not when hydrogen's attached to oxygen, but when hydrogen is attached to oxygen and it's near another item that has water attached to hydrogen, then it's going to form these forces between it, these intermolecular forces called hydrogen bonding. Now you may go, oh, does this happen to anything? No, only between when hydrogen is bonded to fluorine, oxygen, or nitrogen, and is next to another one of those molecules, it's going to form the hydrogen bonds, also called hydrogen bonding. They are the strongest force between molecules, if we're not talking ionic bonding, but between molecules, and get this, it's because of them that the shape of the DNA, y'all know that the shape of DNA looks like a ladder. It doesn't have rungs like you'd put your foot on. Those ladder rungs are actually hydrogen bonds. It's like amazing. All right, well, let's now go to ionic bonding. It's the strongest attractive forces in all because they're not partial charges. They're for real. They are positives and they are negatives. So they're going to form strong crystals. They're going to be solids at room temperature. Notice that salt melts at this very high temperature. Why? Because of its ionic bonding, the strong attractive forces between the ions. So now, let's apply this to something else. The melting points of compounds are related to the strength of the attractive forces between the molecules or compounds. Now, they are lower if you have weak forces like dispersion forces, but they are higher if you have stronger attractive forces such as hydrogen bonding, and they're even highest when you have something so strong like ions in the compound. Now, as we look at table 6.7, this is showing what we just mentioned, that if you have these weak dispersion forces, you have a low melting point. They're all gases way down here. Yet, as we say that, by the time we get to our Br2, notice our Br2. Bromium has 35 electrons, but Br2 is 35 plus 35. So, by the time you do that math, that's 70 electrons. It is actually going to be a liquid at room temperature. It finally has enough electrons. Dipole, but the point is notice there the melting points are going to go higher with more attractive forces. So as we go up with hydrogen bonding, notice with more hydrogen bonding, we're going to have a higher melting point. And by the time we get to ionic bonding, very strong. And you go, what's ionic bond? I already forgot what that is. Well, if the first one's a metal, so magnesium, sodium, they're ionic bonding. So they are going to be solids at room temperature. Now, in table 618, there's a comparison of bonding and attractive forces. You will notice this is another way to view what we were just talking about. That with dispersion forces, it's just weak attractive forces. Whereas dipole, a little bit stronger, and you'll notice this. Hydrogen bonding, much stronger. Hydrogen bond, though, is only when hydrogen is attached to fluorine, oxygen, or nitrogen, and then it can do this between the molecules. And then the strongest of all is our ionic bond. Now, I want you to look at these and identify the main type of attractive forces that are present in these. Like, is it an ionic bond? Is it dipole-dipole, hydrogen bonding, or is it dispersion forces? Press pause and come back right after you also make sure you remember to look at the electronegative chart. All right, so we're back. The first one was asking about N to F. Well, in the electronegative chart, we have N to F, 3.0 and 4.0. That is a dipole. And you go, well, is it an ionic bond? No. So I'm going to start with the strongest. Is it an ionic bond? No. The first one's not a metal. Is it hydrogen bonding? No. Hydrogen is not attached to fluorine, nitrogen, or oxygen. So then, next question is it a dipole? That answer is yes, because we just did this fraction. So it has that. Does it have dispersion forces? Well, it does technically, but they aren't enough. The strongest ones are the dipole-dipole. So technically, you'll notice it says identify the main type of attractive forces. So that's the strongest. Now on H2O, is it an ionic bond? No. Is it a hydrogen bonding? Yes, it can form hydrogen bonds because it is hydrogen that's attached to oxygen. Okay, let's go to C. Br. Is it an ionic bond? No. Is it the hydrogen bonding? No. Is it going to have a dipole? No. Why? Because whatever value Br is, whatever that value is, minus that same value, that's going to be 0. So it's not going to be a dipole. So the only thing it does have is dispersion forces. Okay, KCl. The first one's a metal. Okay, we stop right there. It's a very strong ionic bond. NH3. Okay, is it an ionic bond? Nitrogen is in front, so no. Next strongest is going to be hydrogen bonding. Is there hydrogen bonding that can be had between molecules? Yes, because hydrogen is attached to either nitrogen, hydrogen, or fluorine. Hydrogen attached to nitrogen, oxygen, or fluorine. So that means it can participate in hydrogen bonding. I hope this helps.